All right, open up your book to section 14-5. We're on page 719 in your book. The title of this section is Probabilities of Various Combinations. And our objective here for this section is to calculate the number of different combinations containing R elements taken from a set containing N elements. So this is kind of the other half of the story from the previous section. In the previous section we dealt with permutations, and now in section 14.5 here we're dealing with combinations. So let's start off with what the difference is between the two. We're talking about a combination versus a permutation. So a combination is a collection without regard to order of some or all of the elements in a set. A collection without regard to order. First of all, notice that we're using the word collection here, not an arrangement, like we did with a permutation. And an arrangement indicates that there's an order to it. A collection indicates there's no order to this. So it's a collection without regard to order. In fact, that's the key here. Without regard to order. So another way of describing that is that order does not matter here when we're talking about a combination. Order does matter when you're working with a permutation. So a collection without regard to order of some or all of the elements in a set. All right, you might not be grabbing all the elements from the set. It might be just a subset of it. We saw that same thing with permutation, so that's not the difference between the two. And the example that we started off with in the previous section, we were arranging 3 books out of a group of 7, so we weren't arranging all the books. So it's okay that it's not all of the elements in the set. That's not the difference between the two. The key is that it's without regard to order here for a combination. All right, so how do you go about calculating a combination? Well, here's one way that you could actually calculate it. Since order doesn't matter, we should realize that anytime you are doing a permutation, where order does matter, you're going to get a larger number of permutations or arrangements than you would if you do a combination. And that's because the permutation also includes all the rearrangements of that particular subset that you've grabbed. So to calculate the number of combinations, here's one way you can do it. You could take the total number of permutations, just like we did in the last section, and then divide that by the number of permutations of one given combination. When you divide that out of there, you'll now be left with the number of combinations. You'll have eliminated those repetitions or those repeated arrangements of that particular collection. This is kind of almost like what we did for a repeated permutation. Not quite the same thing that we're dealing with here, but that's kind of the idea there when I see that we're dividing by this number of permutations of one combination. So for example, let's suppose that we want to find the number of letters, find the number of 3-letter combinations from the letters A, B, C, and D. So we've got 4 letters to pick from. And we want to find the number of combinations. So combinations means I don't care about order. I'm just grabbing 3 letters. So if I grab A, B, C, it doesn't matter what order I grab them in. It's just the fact that it's A, B, and C. If I was doing permutations, then the order matters. A, B, C would be different than A, C, B, which is different than B, A, C, and so forth. Order won't matter here. Okay, so for the number of ways of picking 3 letters, oops. So we pick 3 letters. So according to that calculation that we had up above there, I could just calculate the number of permutations of 3 letters. So how many choices do I have for the first letter? Well, there's 4 to pick from, so I have 4 choices for the first letter I pick. These are dependent events, so as I picked one letter, I've now got 1 fewer letter to pick from, so I only have 3 choices for the next and 2 for the last one that I pick. I'm only picking 3 of the 4 letters. That's how many permutations I'd have if I was including the arrangement or the order of those. I'm going to divide out of there the number of ways of permuting or arranging those 3 letters that I picked. So of the 3 letters that I picked, there's 3 choices for the first letter. There are 2 choices for the second letter. And there's only 1 choice for the third letter when I rearrange those 3 letters. So I'm dividing out those arrangements there. So what do we end up with? Well, 4 times 3 times 2. That turns out to be what? 24. And 3 times 2 times 1, that's 6. So 24 divided by 6 is 4. There are 4 combinations. Now again, the numerator of this is the number of permutations. There would be 24 different arrangements of those 3 letters that I picked out of the 4. But in terms of just narrowing it down to how many combinations I have there, just worrying about what letters you pick, not the order that they're picked in, there's only 4 ways to do that. In fact, since there's only 4, we could list them. A, B, and C could be our first choice. And again, if I was doing a permutation, I'd have to say ABC, ACB, BAC, BCA, CAB, and CBA. There'd be 6 different ways of rearranging those. That's why I divided that by 6. All right, so this is one of my combinations. I could pick A, B, and C. I could pick A, B, and D. I could pick A, C, and D. And finally, I could pick B, C, and D. It looks like those are my 4 combinations that I end up with. All right, let's talk about the notation that we can use to represent a permutation. We didn't talk about this in the last section. Let's talk about that now because I definitely want to know how to distinguish between a permutation and a combination. So here's our notation that we're going to use for a permutation from this point forward. The permutation of n elements taken r at a time. So you have n elements to pick from, and you're grabbing r of those and arranging those r things. That's what that's saying there. So n objects total to pick from. You're only going to pick r of them, and you're arranging those. So here's how you can calculate that. First of all, we'll name this NPR. We'll use subscripts for n and r here. Little n, p, and then little r is equal to, it's n factorial divided by n minus r factorial. N factorial divided by n minus r factorial. In fact, that's what we just did there on that previous example there, where we were taking 4 letters and picking 3 of them. It was n factorial, which is actually 4 times 3 times 2 times 1 factorial, divided by n minus r, which is 1 factorial, which is equal to 1. So n factorial divided by n minus r factorial. That's our formula that we'll use to do a permutation. What about a combination? Well, there's actually a couple ways that you can write a combination. Combination, we can call this NCR for combination. By the way, when you're reading those off, you should use the words arrange. You've got n objects and you're arranging those. When you use the word arrange, we're talking about an order there. Versus here we just have a collection when we're talking about a combination. So we can read that off as choosing that many objects. Doesn't matter what order you choose them in, just choose that many. So those are usually the words we use to read those off as. You can actually use the word permute in combination too. So the notation for combinations. This is a combination of n elements taken r at a time. So NCR, and n choose r. Another way that you'll see this written is in a set of parentheses with n over r. That's kind of the shorter hand notation for that. We'll see that in the next chapter, actually, when we talk about the binomial theorem. We'll use that notation. What does that actually mean? Well, this is defined as n factorial divided by r factorial times n minus r factorial. So it's almost the same as the combination, or as the permutation, but realize that we have this one little added piece here. That right there is we're dividing out the number of ways of rearranging those r objects we've picked. That's a permutation right there. In fact, that's what the RPR is equal to. the NPR is the n factorial over the n minus r factorial. That's why these two things are equal to each other. This guy right here is really this part right here. So a combination will just be n factorial divided by r factorial times n minus r factorial. Or if you want to write it as a quotient of two permutations, like we started off with in this section, n arrange r over r arrange r gives us our combination. All right. On your calculator, by the way, if you grab your calculator, I can show you where you have these two values here on your calculator. We'll do an example and use them in just a second. Go ahead and grab your calculator real quick. All right, so if you go under the Math menu again and go over to PROB for probability, right there you'll find above the factorial options NPR and NCR. Those are permutations and combinations. Those are the same things that we're talking about here. That's the reason why we use this notation, is because of the same notation we're going to see our calculator is going to use in some cases as well. So that's our combination and permutation. All right, let's take a look at a couple of examples here now. Actually, I gave us several examples. We're going to skip over example 1 and just jump to example 2. But it says to write NP4 as a ratio of factorials and interpret the answer in terms of the number of elements in the set and the number of elements selected for the permutation. Well, let's first write down what this means as a factorial, and then we can calculate it. And we'll even use our calculator to help us evaluate that as well. So NP4. So first of all, what exactly does that mean? The 9 out front means that you've got 9 objects to pick from. And the 4 means you're going to grab 4 of those and arrange those 4 things that you've grabbed. So you're picking them in order. First object goes first, second object goes second, and so forth. NP4, the arrangement of those 9 objects picked 4 at a time. All right, so our formula then for calculating the permutation, from the formula we just had on the board there, you just take n factorial and you divide it by n minus r factorial. So it's 9 factorial over 9 minus 4 factorial. Or that would be 9 factorial divided by 5 factorial. 9 minus 4. Or you could actually rewrite that, and we could rewrite it, I'll write it down below here, as 9 times 8 times 7 times 6. And it continues 5, 4, 3, 2, 1. But the 5, 4, 3, 2, 1, I could write that as 5 factorial. And why am I going to write it that way? Well, because that's what my denominator has in it, is 5 factorial. Notice that the 5 factorials here would cancel each other out. By the way, sometimes when you're dealing with numbers that are too big for your calculator to handle for factorials, we talked about the limitation that your calculator has with that. Sometimes you have to do this first. Do some simplification first, and then you can calculate what this remaining product is. So really, this is just 9 times 8 times 7 times 6, which is really how we started out these problems in the last sections. We just said, well, if you've got 9 objects and you're picking 4 of them, how many choices do you have for the first one? 9. How many for the next one? 8, 7, and 6. That's what this turns out to be. So we can grab our calculator, and let's evaluate what this is equal to. All right, so I'm going to type in 9 and then go to my Math menu, grab NPR and 4, and press enter, and I get 3,024. In fact, I'll grab a picture of that and put it on that slide. So it's 3,024 is our value. Okay. So if you have 9 objects and you're going to grab 4 of them and arrange 4 of them, I should say, you end up with 3,024 ways that you could do that. All right, take a look at example 3. Same idea, but now we're going to do a combination, right? 9 choose 4 as a ratio of the factorial to a product of factorials. Interpret the answer in terms of the number of elements in the set and the number of elements selected in the combination. Okay. So So 9 choose 4. Now there's a couple of different ways you could write this. You could write it this way, or you could write it in those parentheses like we talked about. But I want to just write it in its factorial form first. So this is equal to 9 factorial divided by, and then it's r factorial, so that's 4 factorial times n minus r. That's 9 minus 4 factorial. Or in other words, this is equal to 9 factorial divided by 4 factorial times 5 factorial. And if you want to rewrite this, you could again do the same thing we did before. That's 9 times 8 times 7 times 6 times, that's really a 5 factorial, divided by 4 factorial times 5 factorial. And again, you'll notice that the 5 factorials cancel each other out here. And so what we have here is really 9 times 8 times, oops, almost looks like a minus here. Let me fix that. 9 times 8 times 7 times 6 divided by our 4 factorial. Remember the 4 factorial here, if you go back to our original slide there where we talked about how to calculate a combination, you're dividing by the number of ways of rearranging these 4 objects that we've picked here. So that's what the 4 factorial is. And of course with 4 factorial, you could rewrite that as 4 times 3 times 2 times 1. And again, you can start canceling some stuff out here to figure out what this is equal to. The 3 times 2 is 6. The 4 would cancel out with an 8 and leave a 2 there. So, this is something that you could potentially still calculate with your calculator here. Don't look at the fact that you got a 9 factorial defined. Instead, simplify that. And now you got something that's manageable to find what this is equal to. But we're going to go ahead and grab our calculator and find out what this is equal to. So go ahead and grab your calculator again, and let's try punching that in. Just clear off that screen. Let's choose 9, and then go to probability, and do NCR. Choose, 4. So 9 choose 4, much smaller number, 126. So the permutation was a much, much bigger number, and that's because of the fact that you're including those rearrangements there. Combination, you have to eliminate those rearrangements. That's why we divided by that 4 factorial. So this turns out to be 126, which 9 times 7 is 63, and then times the 2 that I have in the numerator, yeah, that makes sense that that's a 126. All right, look at example 4. Example 4, now we're going to pick people to make up a committee here. It looks like it's how many different ways could you form a committee of 3 people from a group of 7 people. So you have 7 people to pick from, but you're only going to pick 3 of them. Explain how you know that this is the number of combinations is being asked for, not a permutation. Well, that's the first thing you got to figure out for any one of these problems. Now, the fact that we're talking about combinations in this section should probably be a big hint to you that it's probably a combination problem, but that's not going to help you out on a quiz or a test question here. Make sure you understand why it's a combination for this problem. They're talking about picking any 3 people from a group of 7. Now, if the order mattered that we were picking them in, then it would be a permutation. Maybe we were saying the first person we were picking was going to be the president, and the second person was going to be the secretary, and the next one was going to be the treasurer, or whatever titles we were giving them. Then all of a sudden the order matters because we're assigning them a title as well. But that's not the case in this problem. It just says you're picking 3 people from a group of 7. Order does not matter. That's how I know that it's a combination here. Okay, so the number of ways of picking 3 people from a group of 7. So this is just going to be a combination. I have 7 people to pick from, and I can choose any 3 of them. If it was a permutation, then it would just be 7PR, because I'd have 7 people to pick from, and I'm arranging 3 of them, picking 3 to arrange. So let's go ahead and just grab our calculator and find out what 7 choose 3 is equal to. And again, as long as these are small numbers that we're dealing with, like we have here, your calculator is going to handle this just fine. As these numbers get big, though, you have limitations on factorials, and you're going to have limitations there on combinations and permutations as well. So this turns out to be 35. So there are 35 different ways that we can do that. 7 people to pick from. We're only going to pick 3, 35 different arrangements, or sorry, 35 different combinations of people that we could have on that committee. All right. One last example. Example 5 here. This has quite a bit to it. On page 722, it says, if a committee of 5 is selected at random from a group of 6 women and 3 men. And let's write that down. We got 6 women. I'm going to use W for women and M for men. So we've got 6 women, 3 men. And it says a committee of 5 is selected. So we're picking 5. Six women, 3 men, we're picking 5. So out of the 9 people that are there, we're only picking 5 of them. All right, so for part A, all these say find the probability that it will include the following here. So part A is the probability that it will include Ben and Eileen, which are 2 of the 9 people. I guess we're supposed to make some assumptions here about those names because we have men and women here. So I think we're assuming that Eileen is a woman and Ben is a man, is the category that we're picking those from. I guess they probably should have told us that. They didn't, but anyways, that's the assumption I think that we need to make from this. So we know which category they're in, or which group they're in. All right, so we want to find out the probability that Ben and Eileen, and then we have to pick a total of 5, so we got to pick 3 other people. So it's the probability of picking Ben and Eileen and 3 others. Is what we've got to find, right? So it's a probability, so I'm going to write this out as a quotient here. So the numerator of this is the number of ways of picking Ben, and the number of ways of picking Eileen, and the number of ways of picking 3 others. So this is really the number of ways of picking Ben times the number of ways of picking Eileen times the number of ways of picking 3 others. And we got to divide that by our sample space, which is we're picking 5 people from a group of 9. All right, so it's the number of ways of picking 5. Oops, pick 5 from the 9. 5 people from 9. Okay. All right, so let's calculate then. A number of ways of doing that. Now, we've seen other ways that we could deal with this numerator, but now that we've learned about combinations and permutations and this formal notation, I'm going to write this out using that notation. So let's think about how I can write this as a combination for the number of ways of picking Ben. How many people in the group are named Ben? Well, they didn't tell us that, but I guess we're assuming that there's only one Ben in here. So there's one person named Ben, and I have to pick that one person. So the number of ways of picking the person named Ben, there's one person named Ben, and I have to choose that one person. So it's 1 choose 1. Now that turns out to be 1, is what that's equal to. But I'm writing it this way just so you see how each one of these calculations is done exactly the same in terms of a combination here. Let's multiply that by the number of ways of picking Eileen. Again, how many people are named Eileen? There's one person named Eileen, and we have to choose that one person. So it's 1 choose 1 for Eileen, number of ways of picking Eileen. And then finally, multiply that by the number of ways of picking 3 more people. Well, we've already picked Ben and Eileen, so that's 2 of the 9 people are gone. It didn't tell us whether they had to be men or women here that we picked, so it doesn't matter who we're picking from in terms of that. So out of the 7 people that remain, we have to pick 2 of them. So that means there's 7 people to pick from, and we're choosing 3 of them. 7, choose 3. That last one you definitely need to write as a combination, but I think if you write the first two as combinations, it helps you see how all of these are actually calculated the same way. Just happens to be that 1 choose 1 is equal to 1. All right, we got to divide that by the number of ways of picking 5 people from the 9, so that's, again, a combination. 9 choose 5. All right, so let's grab our calculator and let it help us out here a little bit. 7 choose 3 and 9 choose 5 are the two that we need. Well, I guess we already have 7 choose 3 because we just did that in the previous problem, right? So we know that. Let's just add to this 9 choose 5. And that was that's 126. Which is a calculation we'd done earlier as well. So actually, we kind of already knew the answers that we should come up with here, but that's all right. We've double-checked our answers here, really. All right, so let's write that down. I'm going to leave it just in this form here. Again, if you want to simplify this, you can go ahead and do so, but I like leaving this kind of in its raw form here of 35 out of 126 ways that we can do that. 35 out of 126. All right, let's take a look. That's part A. Let's take a look at part B. Part B now says you want exactly 3 women and 2 men. So we want to find the probability of exactly, what was it, 3 women? 3 women and 2 men. All right, so again, it's a probability, so we're going to write this as a quotient. So what I need to do is find out the number of ways of picking 3 women and the number of ways of picking 2 men. So those are going to be either independent or dependent events. So we're multiplying these together. The word and is what I'm looking at there. But of course, I've got 2 different groups here. You're either in the men or the women group there is what we're saying here for this problem. So these are going to be independent events here. So number of ways of picking 3 women times the number of ways of picking 2 men. And we're going to divide that by the same thing, the number of ways of picking 5 people, right? I'm just going to say pick 5. Oops, pick 5 from the group of 9, right? Okay, so let's calculate those. And again, I'm going to write these as combinations as we do this. The order that I pick them in does not matter. I just need to get 3 women. So there were a total of, what, 6 women to choose from? Yeah, 6 women they gave us from to pick from. And we've got to choose 3 of them. That's the number of ways of choosing 3 women out of the group of 6. And we have to pick 2 men from the group of 3. So there's 3 men to pick from, and we're going to choose 2 of them. So 6 choose 3 times 3 choose 2. And again, it's all divided by the same 9 choose 5. 9 people to pick from, and we got to pick 5 of them. All right, so let's let our calculator help us out here again. We've already done that 9 choose 5 here, so we have that one, but let's calculate the other 2. 6 choose 3 and 3 choose 2. 6 choose 3 and 3 choose 2. Now that's probably one we should be able to think about what that actually means. You have 3 people to pick from, and you're going to pick 2 of them. How many different ways can you do that? There should only be 3 ways that we can make that happen. That's what we get. All right, so we end up with 6 choose 3 was 20 times 3 choose 2 we said was 3 divided by the 126 that we got before. I think that was what the 9 choose 5 was. I said we done, yeah, that was the 126. We did it before. I just wanted to make sure I got the right number. So that's 60 over 126, almost a 50-50 chance that that's going to happen. 63 out of 126 would have been exactly a 50% chance of that occurring. All right, one last example here. Look at part C. Part C now throws in the word at least. It says the probability that you have at least 3 women. Probability of at least 3 women. All right. So if you want to have at least 3 women on our committee of 5 people, that means you could have 3 women on there, you could have 4 women on there, or you could have all 5 women on there. So it's the number of ways of picking 3 women, and then of course 2 men to fill the committee of 5. That's the first option. Or, and the key is the word or, so we're adding this to the number of ways of picking 4 women and then 1 man. Or, so that's we're adding to that the number of ways of picking all 5 are women, and that means we have 0 men on that committee. And again, that's all divided by the number of ways of picking 5 people from our group of 9. All right, so let's figure out what each of these are. So the number of ways of choosing 3 women and 2 men. So you've got 6 women to choose from, and you want to pick 3 of them. That gets your 3 women. You've got 3 men to pick from, and you want to choose 2 of them. That's the calculation we actually just did on the previous part. Now we have to add to that the committee of 4 women. So we have 6 women to choose from, and we're picking 4 of them. And we have 3 men to pick from, but I only want to choose 1 of them. And finally, I have to add that to the committee of just 5 women. So I've got 6 women to choose from, and I'm going to pick 5 of them. I've got 3 men to pick from, but I'm going to choose none of them. Again, even though we technically don't need to worry about that part of it, I'm writing it that way just so we see we're doing the exact same calculation for each one of these things. 3 choose 0. If you have 3 men to pick from and you're going to pick none of them, there's one way to do it. Don't pick anybody. So we know what that last calculation is going to be, but still write it down just so it kind of makes sense for how we're writing out the rest of this problem, and to notice that it's not some special case there at the end. All these are being done the exact same way. All right, we've done actually quite a few of these calculations already, so I think we can write most of these down here. We know 6 choose 3 was the 20. 3 choose 2 was the 3. 6 choose 4. We're going to have to grab our calculator and punch that in. I'll let you grab your calculator and check to see what you end up with that. 6 choose 4, though, it should be 15, I think, is what we should end up with. You can check that on your calculator. 3 choose 1, there's 3 ways to do that. 6 choose 5, there's only 6 ways to do that. And 3 choose 0, again, that's 1. This is all divided by 126. Again, you can run that through your calculator and see what you end up with and make sure you're getting the same results, but I think you'll see you get the same results I've got here. Okay, so let's add this up. 20 times 3 is 60. 15 times 3 is 45, so that's 105. And then 6 more at the end should be 111. So there's 111 ways that we could pick at least 3 women out of 126 possible combinations there. High probability that you'll have at least 3 women on the committee is what that means. All right, that right there is the end of section 14.5.